Zeolites are microporous, aluminosilicate minerals commonly used as commercial adsorbents and catalysts. The term zeolite was originally coined in 1756 by Swedish mineralogist Axel Fredrik Cronstedt, who observed that upon rapidly heating the material stilbite, it produced large amounts of steam from water that had been adsorbed by the material. Based on this, he called the material zeolite, from the Greek zeta epsilon omega, meaning to boil, and lambda iota theta omicron sigma, meaning stone. Zeolites occur naturally but are also produced industrially on a large scale. As of July 2015, 229 unique zeolite frameworks have been identified, and over 40 naturally occurring zeolite frameworks are known. Properties and occurrence. Zeolites have a porous structure that can accommodate a wide variety of cations, such as Na+, K+, California 2+, Mg2+, and others. These positive ions are rather loosely held and can readily be exchanged for others in a contact solution. Some of the more common mineral zeolites are enalcima, shabazite, clinoptilolite, hewlandite, natrolite, philipsite, and stilbite. An example of the mineral formula of a zeolite is Na2 aluminium silicide O10-H2O, the formula for natrolite. Natural zeolites form where volcanic rocks and ash layers react with alkaline groundwater. Zeolites also crystallize in post-depositional environments over periods ranging from thousands to millions of years in shallow marine basins. Naturally occurring zeolites are rarely pure and are contaminated to varying degrees by other minerals, metals, quartz, or other zeolites. For this reason, naturally occurring zeolites are excluded from many important commercial applications where uniformity and purity are essential. Zeolites are the aluminosilicate members of the family of microporous solids known as molecular sieves. The term molecular sieve refers to a particular property of these materials, i.e., the ability to selectively sort molecules based primarily on a size exclusion process. This is due to a very regular pore structure of molecular dimensions. The maximum size of the molecular or ionic species that can enter the pores of a zeolite is controlled by the dimensions of the channels. These are conventionally defined by the ring size of the aperture, where, for example, the term 8-ring refers to a closed loop that is built from 8 tetrahedrally coordinated silicon atoms and 8 oxygen atoms. These rings are not always perfectly symmetrical due to a variety of effects, including strain induced by the bonding between units that are needed to produce the overall structure, or coordination of some of the oxygen atoms of the rings to cations within the structure. Therefore, the pores in many zeolites are not cylindrical. Zeolites transform to other minerals under weathering, hydrothermal alteration, or metamorphic conditions. Some examples. The sequence of silica-rich volcanic rocks commonly progresses from clay quartz mordanite hewlandite epistilbite stilbite thomsonite mesylite scalacite shabazite calcite. The sequence of silica-poor volcanic rocks commonly progresses from calcite levine ophrotite enalcima thomsonite mesylite scalacite shabazite calcite. Production. Industrially important zeolites are produced synthetically. Typical procedures entail heating aqueous solutions of alumina and silica with sodium hydroxide. Equivalent reagents include sodium aluminate and sodium silicate. Further variations include changes in the cations to include quaternary ammonium cations. Synthetic zeolites hold some key advantages over the natural analogues. The synthetic materials are manufactured in a uniform, phase-pure state. It is also possible to produce zeolite structures that do not appear in nature. Zeolite A is a well-known example, since the principal raw materials used to manufacture zeolites are silica and alumina, which are among the most abundant mineral components on Earth. The potential to supply zeolites is virtually unlimited. Natural occurrence conventional open-pit mining techniques are used to mine natural zeolites. The overburden is removed to allow access to the ore. The ore may be blasted or stripped for processing by using tractors equipped with ripper blades and front-end loaders. In processing, the ore is crushed, dried, and milled. The milled ore may be air-classified as to particle size and shipped in bags of bulk. The crushed product then may be screened to remove fine material when a granular product is required, and some pelletized products are produced from fine material. As of 2016, the world's annual production of natural zeolite approximates 3 million tons. Major producers in 2010 included China, South Korea, Japan, Jordan, Turkey, Slovakia, and the United States. The ready availability of zeolite-rich rock at low cost and the shortage of competing minerals and rocks are probably the most important factors for its large-scale use. According to the United States Geological Survey, it is likely that a significant percentage of the material sold as zeolites in some countries is ground-sawn volcanic tuff that contains only a small amount of zeolites. Some examples of such usage include dimension stone, lightweight aggregate, pozzolanic cement, and soil conditioners. Artificial synthesis. There are several types of synthetic zeolites that form by a process of slow crystallization of a silica-alumina gel in the presence of alkalis and organic templates. One of the important processes used to carry out zeolite synthesis is sol-gel processing. The product properties depend on reaction mixture composition, pH of the system, operating temperature, pre-reaction, seeding time, reaction time, as well as the templates used. In sol-gel process, other elements can be easily incorporated. The silicality salt formed by the hydrothermal method is very stable. The ease of scaling up this process makes it a favorite route for zeolite synthesis. Uses. Zeolites are widely used as ion exchange beds in domestic and commercial water purification, softening, and other applications. In chemistry, zeolites are used to separate molecules, and as traps for molecules so they can be analyzed. Zeolites are also widely used as catalysts and sorbents. The well-defined pore structure and adjustable acidity make them highly active in a large variety of reactions. Zeolites have the potential of providing precise and specific separation of gases, including the removal of H2O, CO2 and SO2 from low-grade natural gas streams. Other separations include noble gases N2, O2, freon and formaldehyde. On-board oxygen-generating systems and oxygen concentrators use zeolites in conjunction with pressure swing adsorption to remove nitrogen from compressed air in order to supply oxygen for aircrews at high altitudes, as well as home and portable oxygen supplies. Industry. Petrochemical industry. Synthetic zeolites are widely used as catalysts in the petrochemical industry, for instance in fluid catalytic cracking and hydrocracking. Zeolites confine molecules in small spaces, which causes changes in the structure and reactivity. The hydrogen form of zeolites are powerful solid-state acids, and can facilitate a host of acid-catalyzed reactions, such as isomerization, alkylation, and cracking. The specific activation modality of most zeolitic catalysts used in petrochemical applications involves quantum chemical Lewis acid site reactions. Catalytic cracking uses reactor and a regenerator Feed is injected onto hot fluidized catalyst where large gas oil molecules are broken into smaller gasoline molecules and olefins. The vapor phase products are separated from the catalyst and distilled into various products. The catalyst is circulated to a regenerator where air is used to burn coke off the surface of the catalyst that was formed as a byproduct in the cracking process. The hot regenerated catalyst is then circulated back to the reactor to complete its cycle. Nuclear industry. Zeolites have uses in advanced reprocessing methods, where the microporous ability to capture some ions while allowing others to pass freely, allowing many fission products to be efficiently removed from nuclear waste and permanently trapped. Equally important are the mineral properties of zeolites. Their aluminosilicate construction is extremely durable and resistant to radiation even in porous form. Additionally, once they are loaded with trapped fission products, the zeolite waste combination can be hot pressed into an extremely durable ceramic form, closing the pores and trapping the waste in a solid stone block. This is a waste form factor that greatly reduces its hazard compared to conventional reprocessing systems. Zeolites are also used in the management of leaks of radioactive materials. For example, in the aftermath of the Fukushima Daiichi nuclear disaster, sandbags of zeolite were dropped into the seawater near the power plant to adsorb radioactive cesium which was present in high levels. Biogas industry. The German group Fraunhofer e.V. announced that they had developed a zeolite substance for use in the biogas industry for long-term storage of energy at a density 4x more than water. Ultimately, the goal is to be able to store heat both in industrial installations and in small combined heat and power plants such as those used in larger residential buildings, commercial and domestic heating and refrigeration. Zeolites can be used as solar thermal collectors and for adsorption refrigeration. In these applications, the high heat of adsorption and ability to hydrate and dehydrate while maintaining structural stability is exploited. This hygroscopic property, coupled with an inherent exothermic reaction when transitioning from a dehydrated to a hydrated form, make natural zeolites useful in harvesting waste heat and solar heat energy. Zeolites are also used as a molecular sieve in cryosorption-style vacuum pumps. Detergents. The largest single use for zeolite is the global laundry detergent market. This amounted to 1.44 million metric tons per year of anhydrous zeolite in 1992. Cat litter. Non-clumping cat litter is often made of zeolite or diatomite. Construction. Synthetic zeolites are used as an additive in the production process of warm-mix asphalt concrete. The development of this application started in Germany in the 1990s. They help by decreasing the temperature level during manufacture and laying of asphalt concrete, resulting in lower consumption of fossil fuels, thus releasing less carbon dioxide, aerosols, and vapors. The use of synthetic zeolites in hot mixed asphalt leads to easier compaction and, to a certain degree, allows cold weather paving and longer hauls. When added to Portland cement as a pozzolan, they can reduce chloride permeability and improve workability. They reduce weight and help moderate water content while allowing for slower drying, which improves brake strength. When added to lime mortars and lime metakaolin mortars, synthetic zeolite pellets can act simultaneously as pozzolanic material and water reservoir. Gemstones. Thomsonites, one of the rarer zeolite minerals, have been collected as gemstones from a series of lava flows along Lake Superior in Minnesota and to a lesser degree in Michigan. U.S. Thomsonite nodules from these areas have eroded from basalt lava lava flows and are collected on beaches and by scuba divers in Lake Superior. These Thomsonite nodules have concentric rings in combinations of colors black, white, orange, pink, purple, red, and many shades of green. Some nodules have copper inclusions and rarely will be found with copper eyes. Quote, when polished by a lapidar, the Thomsonites sometimes display a cat-sun effect. Biological, medical, research into and development of the many biochemical and biomedical applications of zeolites, particularly the naturally occurring species heulandite, clinoptililite and scherbazite, has been ongoing. Zeolite-based oxygen concentrator systems are widely used to produce medical-grade oxygen. The zeolite is used as a molecular sieve to create purified oxygen from air using its ability to trap impurities, in a process involving the adsorption of nitrogen, leaving highly purified oxygen and up to 5% argon. Quick-clot brand hemostatic agent, which is used to stop severe bleeding, contains a calcium-loaded form of zeolite found in kale and clay. Agriculture. In agriculture, clinoptililite is used as a soil treatment. It provides a source of slowly released potassium. If previously loaded with ammonium, the zeolite can serve a similar function in the slow release of nitrogen. Zeolites can also act as water moderators, in which they will absorb up to 55% of the weight in water and slowly release it under the plant's demand. This property can prevent root rot and moderate drought cycles. Clinoptililite has also been added to chicken food. The absorption of water and ammonia by the zeolite made the birds' droppings drier, less sodoriferous and hence easier to handle. Aquarium keeping. Pet stores market zeolites for use as filter additives in aquaria. In aquaria, zeolites can be used to adsorb ammonia and other nitrogenous compounds. However, due to the high affinity of some zeolites for calcium, they may be less effective in hard water and may deplete calcium. Zeolite filtration is used in some marine aquaria to keep nutrient concentrations low for the benefit of corals adapted to nutrient-depleted waters. Where and how the zeolite was formed is an important consideration for aquaria. Most northern hemisphere natural zeolites were formed when molten lava came in contact with seawater, thereby loading the zeolite with sacrificial ions. The mechanism is well known to chemists as ion exchange. These sodium ions will speciate with other ions in solution, thus the take-up of nitrogen in ammonia, with the release of the sodium. A deposit near Bear River in southern Idaho is a freshwater variety. Southern hemisphere zeolites are typically formed in freshwater and have a high calcium content. Zeolite filters ammonia effectively, but must be used with some care, especially with delicate tropical corals that are sensitive to water chemistry and temperature. Zeolite mineral species. The zeolite structural group includes 09 gauge zeolites with T5010 units, the fibrous zeolite natrolite framework, gonadite, natrolite, mesnolite, paranatrolite, scholasite, tetranatrolite, eddingtonite framework, eddingtonite, calbauxite, thomsonite framework, Thomsonite series, 09 GB, chains of single-connected four-membered rings, analcima framework, analcima, lucite, pellucite, wierarchite, lomontite, ugawarolite, goosecrickite, montesumate, 09 GC, chains of doubly connected four-membered rings, phillipsite framework, harmotome, phillipsite series, gismandine framework, amosite, gismandine, garonite, gobinsite, bogosite, merlinoite, mazite series, paulingite series, perlealite, 09 GD, chains of six-membered rings, tabular zeolites, scherbazite framework, phaeusite framework, phaeusite series, lin-type 10, lin-type Y, mordanite framework, maricopa et, mordanite ophrotite, wenkite subgroup 09 GD. 25. Ophiolite, Wenkite, Bilbergite, Bickitite, Arianite series, Ferrierite, G-Melionite, Levine series, Daciadite series, a stilbite, 09, GE, chains of T1020 tetrahedra Heulandite framework, Clinoptilolite, Heulandite series, Stilbite framework, Barrerite, Stellarite, Stilbite series, Brewsterite framework, Brewsterite series. Others: calcite, pentosil, chinicite, Lin type A framework.